next topic, which is on grains and grain boundaries. We have already said that most of the materials are engineering materials happens to be polycrystalline materials. They are multi-grain materials. Our earlier discussions have been about single grain materials, and let us see what happens when we say that there are a number of grains. Obviously, then there are regions where those grains are joining each other, which are called as grain boundaries. How do you identify them? How do you name them? What are various types of grain boundaries? That is what we intend to study here. Okay, so we have already, if you remember our last class, we have talked about the Schmidt's law. So this is basically what you get from uh, the Schmidt's law, which we say describes the plastic deformation of single crystals. So we said that single crystals, we can use Schmidt's laws to find out what is the sigma y value, what is the tau CRSS value, and how they are related through this vector cos phi cos lambda, which we say is nothing but called as the Schmidt's vector. Okay, so this is what is happening there. If you're taking a single crystal and loading it in a direction perpendicular to this, in this direction, and you are saying that you are applying a normal stress sigma here, it is understood here that from our basic mechanics of materials that your maximum shear stress will be acting at an angle, when we say this is 45 degrees, and then at that time the resolved shear stress along these planes, which we say can be slip planes, will be having the value of sigma by 2. Or I can say here that sigma y can be related to as 2 times tau CRSS, that is critically resolved shear stress. But now the things become different when we talk about a polycrystalline material. So what you have is a material now which has a number of grains. It is not a single crystal material, so it is showing here there are a number of grains here. So one of them is having this orientation. That's what you're saying, that the slip planes may be oriented in this direction in one of the grains. In the second one, they may be oriented in a different direction. In the third one, they may be oriented in a separate direction, maybe this way. We are not sure, but still I can comment upon that. Okay, that they will be different. That is why they are called as different grains, because they have got different orientations. So what you have is that the unit cells were growing separately, and then obviously that they have got different unit cell orientations, and that is why the orientation of the slip planes will always be different along different in these grains also. So for each grain we can find here that when you apply same value of sigma here on a polycrystalline material, each of the grains is actually getting oriented slip planes in each of the grains is getting oriented at different times, and that is why we find here that the behavior will not be simply given by Schmidt's law, which is just giving us the basics about the what we call as a plastic deformation of single crystals. Now coming to the concept of grain boundaries. So what do you understand by that? So the definition says it's a interface between the two grains or crystallites or crystals. I can say that, as I said already, that grains and crystals, they mean the same thing to us. So it can be the interface between the two grains or crystallites in a polycrystalline material. So when you see here that these are what we call as grain boundaries, because they have this is a polycrystalline material. And what is happening here? This is just an enlarged view of one of the regions here. So you can see that this one is the grain boundary here. This is one grain boundary. Another one is here, and another one is, let us say, here. And if I look at that carefully, what you're trying to show here is a crystal lattice. Maybe it is shown in a 2 dimensions, but it will be actually in 3-dimensional ones. But right now, just to make us understand easily, we are just showing here that the crystal lattice is shown here is in 2 dimensions. And we are saying that these are individual crystals here. So these are crystal number 1, this is grain number 2, this is grain number 3, this is grain number 4. And we see here that the unit cells in the grain number 1, 2, 3, 4, they are oriented separately. They are oriented separately. So they are oriented in this direction, separately here, and separately here. And that is why you create a region in between where because they start growing during solidification, and once they start growing in different directions, ultimately they have to meet at some place. So once they start merging with each other, there are these regions which we say are called as irregular regions. The regions which are irregular in terms of crystal lattice, or I can say here the perfection of the lattice is lost. The perfection of the lattice is lost in these regions, which are called as actually grain boundaries. Where two grains are actually meeting, or it's an interface region. It's an interface region between the two grains. So one grain, two grain, in between that is an interface region, which we say will be termed as a grain boundary. And in a two-dimensional scenario, or even in a 3D scenario also, right now what we observe is that a grain boundary is nothing but it can be termed as a rotation boundary. I will just explain it in a minute, that what is the meaning of this term. The next line explain it. The grain on one side of the grain boundary is rotated with respect to the grain on the other side of the grain boundary. So this is very clear here. So you have the grain number 1 here. It is in this orientation. Let us see. And we say now we have a grain boundary here, and this is the grain number 2, which is growing in a different direction. So your grain number 1 and 2, they are rotated with respect to each other. So grain on one side of the grain boundary is rotated with respect to grain on the other side of the grain boundary. So that is why a grain boundary is also referred to as a rotation boundary. So now when I say the grain on one side is rotated with respect to the other side, that means there are two terms which will be known to us, which can be actually termed here with this rotation. We say that one of it is the rotation axis, the axis around which these two grains are rotated. And second is the rotation angle, that what is the angle of rotation between the two grains. So keep it in mind, grain boundaries are what? Rotation boundaries, means the grain on one side of the boundary is rotated with respect to the grain on the other side of the grain boundary. Second thing, once I say we are talking about rotation, we must be knowing what is the axis of rotation, what is the axis around which this rotation is taking place. And second is how much is the rotation, that is I shall quantify this rotation, that is rotation angle. And we will try it, and this is the basis of classification of grain boundaries, the rotation axis, and we will see how do you classify that.